Alrighty, so here we are with 12.4, which is talking about inscribed angles. And so our objectives today are to find the measure of an inscribed angle and to use inscribed angles and their properties to solve problems. So basically we're going to have quite a few theorems today, and then we'll do examples right after each theorem. So remember that all the theorems are going to be in your packet. So this packet, of course, can be used on quizzes and tests. So that's the Chapter 12 theorem packet. And so all of the ones, if you're looking ahead, that we are going to do today here are these right here. All right. So the first set of ideas that we are going to do today is understanding what an inscribed angle is. So what we've been doing up until now is a central angle. So taking a look at what we have here, this would have been, our central angle, because it comes from the center. Now this center or vertex dot is actually going to be on the circumference of the circle. So again, no longer central, and so no longer equal, but actually it's going to be half. So inscribed angle is an angle whose vertex, so again that's this point E here, is on a circle and whose sides contain chords of the circle. So again, looking at here, DEF is an inscribed angle because E is its vertex, it's on the circle, and its sides, DE and EF, are chords. All right. The intercepted arc consists of endpoints that lie on the sides of an inscribed circle and all the points of the circle between them. So these endpoints, meaning D and F, are part of the intercepted arc, which is arc DF. So DF is the intercepted arc because this angle, if you imagine it, kind of cuts into the circle piece right here. So this is the intercepted piece. All right, then we have subtend, and subtend is when lines or points coincide with, between two arcs or angles. So DF, for instance, this part here, arc DF, subtends DEF because they coincide. All right. So those are three of our new terms. And so we're going to start on our theorem. So the first theorem here is technically 11.4.1, but we don't necessarily reference it as that. This one actually tends to be referenced as the Pac-Man Theorem. Perhaps you can see why. If you look at, especially this one, for instance, you can kind of see your little Pac-Man guy. Or, Pac Lady. Because, of course, if you put a bow on it, that somehow means that it's a lady. Okay, so anyway, Pac-Man Theorem. The idea of that is that the measure of an inscribed angle is half, kind of referenced this already, the measure of its intercepted arc. So again, angle is half of the arc. So, for instance, if we know that this arc measure is 80, then we know that this is 40. All right. Same thing here, even if the line doesn't go through the center, one of the sides doesn't go through the center, all right, or if they don't even straddle the center piece. So that's your Pac-Man theorem. Alrighty. So using that theorem, we're going to find each measure. So we're going to find an angle first here, PRU, which is this one. And as I just referenced in the previous one, notice that this angle is in reference to this arc measure. And so if we divide this arc measure by 2, we will get this angle measure. So PRU comes from 118 divided by 2. And so we get 59 degrees. All right. All right, the next thing is the opposite of that. So they're saying that 27 degrees is this angle measure. And so if that's 27, go ahead and multiply by 2, and we're going to get the measure of PS. So the measure of PS or SP is going to come from 27 times 2, and so we're going to be at 54 degrees. All right. And again, remember this is an arc measure, not an arc length, and so we are talking about degrees. All righty. The next piece here is a corollary. Again, that means that it's very closely related to the Pac-Man theorem, and so kind of imagine a bunch of Pac-Mans happening around in here. The idea is that if an inscribed angle of a circle, what does it say? Intercepts the same arc or are subtended by the same chord, or arc, then the angles are congruent. So that technically means that if we take a look at each of these specifically, this angle, notice, intercepts arc AB, right? But this angle as well intercepts arc AB. And then this angle also intercepts arc AB. And so it turns out that every single one of these angles, since it intercepts the same arc, would be found doing the same math. Like, for instance, if this was 118, like our last example, each of these would be half of that 118, so 59. So that's what this is saying here. They're saying that each of the angles is equal because of this arc being shared. All right. So now we have a little art student problem here, and they are turning in an abstract design for this art project, and we need to find DFA. DFA. I'm not going to do it that way. So we need to find this angle measure. So there is kind of a lot to look at here, but the first thing that you can see is that they're giving this angle measure of 33. I'm just double checking where that arrow is going. That arrow points to this entire set of angles as 33 degrees. So taking a step back from that picture, if this is C and it intersects, it looks like, with D, and then over here with A, if this is 33 degrees, then this out here is 66 degrees. Okay. So that intercepted arc from D to A is 66 degrees. Let's see what else we can find out. We also then know that this angle measure is 33 degrees. Again, trying to find this piece. How can I get to that center? It's not even a center. Nope. All right. So I know it has to do with a triangle that's in here. So where is our triangle? I know we want to pretend it's half, but we can't pretend it's half for 33. Oh, hi, there's 164 right here. So that means that this angle measure of CEB, so drawing another diagram for ourselves, E out to C, and then out to B, encompasses 164 degrees. And so if this arc is 164, half of that arc is going to be this angle measure here. So half of 164 is 82. So we know that this angle up here is 82, C and B. And now we need this measure here. So let's see. That's a circle. Nope. Oh. So along with that being 82, we also know that if this is A and it goes to C and B as well, then angle A is 82. We also know that angle D that intercepts C and B as well is also 82. So we have an 82 for here. And so if we want to find that angle, I can now take this triangle of FAB, which is fabulous. And A, we just said, was 82. B, we already said, was the same as C. So B is 35. And then they're all going to add up to 180. So 180 minus 82 minus 35 gets 63 degrees. Turns out the same triangle opposite that makes this 63 degrees as well. And so, since these are on a line, this would extend out. And we are trying to find DFA, that's this one here. They're on a line together with 63. So to find angle DFA, we're going to take 180 and subtract 63 and get 117. Now, was there an easier way to go about that? I assume so. However, this is the way that I figured it out. So, again, angle B was 35, and then it formed a triangle with 35 and A and F, and then those two form a line together, and so that's how we're getting 117. All right. Notice how I worked this through was that I took pieces from this and not necessarily this exact diagram. I suppose I could have made this huge and been able to write inside of it, but because I couldn't, if you take little pieces from the big diagram, it will work out a little better in the end. All right. So then we move on to this theorem that puts a right triangle inside of the circle. So Theorem 1143 talks about this diameter of this circle being actually the hypotenuse of a right triangle. So an inscribed angle subtends a semicircle if and only if the angle is a right angle. And again, this is saying that the diameter is equal to the hypotenuse. All right, so taking a look at that theorem, we do not necessarily have it in here, and that's usually how these right angles work. But again, notice this is a diameter, and so when you see a diameter, this is assumed to be 90 degrees. And so officially, if we want to find A, or in this case, part of angle Z is equal to 90 degrees, and it's also equal to 5A plus 20. So that means that we can algebraically solve for angle Z by moving this 20 over with this 90 and dividing by 5 to get an A value of 14. And again, they just wanted the A value. So again, looking at this object, we do technically have what looks like an inscribed angle, okay? But because of that, this would have been 180, which makes this 90. So either way, 5A plus 20 should have equaled 90 degrees. All right, moving on. Our next inscribed angles theorem has to do with a four-sided shape inside or inscribed, which means exactly touching at these points only. A four-sided shape. So if a quadrilateral is what goes here, is inscribed in a circle, then its opposite angles are supplementary. So that means, at least in our conclusion here, that A plus C equals 180 degrees. We also know that D plus B is 180 degrees as well. Of course, they would all add to 360 like any other four-sided shape, but for specific pieces here, the opposite angles are supplementary. So our last example goes ahead and uses that idea. And so, for instance, we need to find all of the measures, G, H, J, and K. But to do that, this opposite angle with this opposite angle should add to be 180. So algebraically, I should have 6B plus 20 plus the other angle, which is 3B plus 25, and that should equal 180. So going through and solving that, combining some like terms here, 9B's plus 45 should equal 180. Move your 45 over. And 9B's should equal 135. Divide by 9, and you should have a B value of something. 15. So they do want you to find all of the angle measures. So now that we know what B is, we could at least plug it in here, here, and here to get your measure of your angles. So for instance, angle G is going to be 3B plus 25, but instead of a B, we're going to put 15. So 3 times 15 plus 25. So angle G is 70 degrees. We also have angle J here. And it should be supplementary with 70, so we can kind of see that it should be 110. But algebraically, it's 6 times 15 plus 20. So 6 times 15 is 90 plus 20 is 110. All right. Then we have angle K here, which still uses B as its variable. So 10 times 15 minus 69 should be our answer. Should be our angle measure for that one. So 150 minus 69 is 81 degrees. And then remember that our opposite angles, so K and H, should also add to be 180 degrees. So, 1 second, minus. All right. So if we want to find angle H, we should just take 180 minus angle K, or 180 minus 81. And we'll get 99 degrees for this missing angle. So of course they can't just tell you what each of them is with a B. They needed to, in the end, not have a B here so that you could remember, yes, this, once I found the angle, should add with this to be 180. So there we are, inscribed angles. Again, the newest concept here is that Pac-Man idea that if you have an inscribed angle, meaning you have the vertex on the outside of the circle now instead of the inside, you now have half of this arc measure as the angle measure instead of equal. All right. Hopefully that worked out and you are ready for the assignment.